Welcome back to the latest lecture session on alkalinity and relevant aspects. We were looking at alkalinity in the context of coagulation, right? And why is it? Because when we add metals, they take up OH minus, let's say, right? And thus you are going to see a decrease in pH, and that's something you don't want. So we were looking at alkalinity, and typically alkalinity is given by the carbonate species, right? CO3 2 minus, HCO3 minus and such. And let's get right in. So alkalinity, theoretical definition, assuming that there are no other species, we list all the bases, OH minus and the other bases which are usually present, HCO3 minus and CO3 2 minus, right? And because CO3 2 minus can take up 2 H plus, so there is this 2 because this is the equivalence, and minus H plus obviously, I guess, right? And here the units are in molar units. Yes, and this units of alkalinity, because it's a relative term, will be in equivalents per liter or such. Alkalinity can also be expressed as CaCO3 as milligrams of CaCO3 per liter. Again, this is equivalents, let's see, right? So again, the units will not be in terms of milligrams of alkalinity. There is no such thing as compound alkalinity, right? Milligrams of alkalinity, but it will be expressed in terms of either equivalents per liter or in terms of CaCO3, as in how much CaCO3 do I need to add to get this required amount of alkalinity. That is what this aspect as CaCO3 or as milligrams of CaCO3 per liter means, right? So that's something to keep in mind. Without it, let's see what can happen and why alkalinity is required. If sufficient alkalinity is available, Al3 plus and HCO3 minus, well, it's written in a different form. So net, we are assuming here that there is no decrease in pH. But if there is no alkalinity available, here we are saying that alkalinity primarily HCO3 minus. Why? If the pH is at 7, what will this equation, or near about 7, what will this equation transform into? OH minus and H plus will cancel out because the pH is 7. And you know from this graph, this is the pH. I am just drawing the speciation diagram for the relevant carbonate species, right? So let me just label that so that it's much more clearer. So this y-axis is the relative concentration, and this will be the pKa. This is 6.3, pKa1, because it's diprotic H2CO3, right? This will be 10.3. So below 6.3, H2CO3 will predominate. Between 6.3 and 10.3, HCO3 minus will predominate, and above 10.3, CO3 2 minus will predominate, right? Above pH of 10.3. These are the two pKa values, pKa1 and pKa2, acid dissociation constants. Obviously, as you see, near around 7, most of it will be present as HCO3 minus. So in general, you can assume that alkalinity is equal to or approximately equal to HCO3 minus concentration when the pH is 7. Again, if alkalinity is present, this is what will happen. If not, you will have this being formed, but H2SO4 will not stay as H2SO4. It will immediately dissociate into 2H plus and SO4 2 minus, let's say, right? H2SO4 will dissociate. Why? It's a very strong acid, pKa is pretty less. It might not go to 2H plus, it will go to H plus and HSO4 minus, and then H plus and SO4 2 minus. Again, H plus will be released, and then the pH is going to decrease. So that's why alkalinity is required, let's say, right? So coagulation using alum, right? In that context, we were discussing these aspects, and we already discussed this aspect, need to add alkalinity. Some cases you will want to not do that, because low pH can lead to help remove NOM because of change in charge, right? So solubility of alum salts. Why am I looking at this? Because we mentioned earlier that this particular metal or some of the metals will not stay as free metal, right? They will be in equilibrium with complexes and also what else? The solid or the precipitate, let's say, right? So they will be in, maybe this I should not draw here, they will be in equilibrium, let's say, right? It's a fine balance between these three. Yes. So let's see in which pH ranges which one will predominate and such. So here we have x-axis pH and on the y-axis the concentration of the metal. Please note that the concentration of metal is pretty low and this seems to be logarithmic scale, let's see, right. So you can get the log C pH relevant lines. Let's say for Al3 plus, looks like the, if I do the relevant analysis, it's going to be depend upon 10.8 minus 3 pH. Again, I will not go there, but you can see the relevant aspects, but let's just look at the figure. So at relatively low pH and relatively low concentration or very low concentration, the metal will stay as free metal Al3 plus. Even at relatively low pH but higher metal concentration, it will stay as AlOH4 minus, right. But in general, this will also take place later also, but again let us not go there. But in the neutral pH and in the usual concentrations that we add, what is the form that predominates? You can see that this is the form in the neutral pH range and in the metal usual metal concentration that we add, you see that most of it will stay as the, or will precipitate as the solid. And if I increase the pH further, then you can have either the solid or the complex here, right. So that depends on the concentration and such. Again, this is the predominant form. It does not mean that at pH 7 and a concentration of 10 power minus 4 everything will be as the solid, but it means that the predominant form of aluminum will be this. This is called a predominance area diagram. It will only give you an idea about in which pH or under which pH range and under what concentrations will you have will the kind of complex or precipitate or the metal predominate. So predominance area diagram, let's see, right. So that's what you have. You see that at higher pH range, obviously more OH minus available and you are having complexes, and relatively low concentrations and pH, mostly the metal, but at the usual working range, the predominant one is the metal that's being formed. And now you can look at this. Here we have operating region for the aluminum salts when we are talking about coagulation. So here is the pH from 0 to 14 and the concentration of the aluminum logarithmic scale, right. Here we are increasing the concentration as we go along there and pH is increasing as we go along there, right. So as you can see, this figure is relatively similar to the predominance area diagram. Why? Because depending upon the type of aluminum that predominates at that particular conditions of pH and aluminum concentration, you are going to have either charge neutralization or sweep coagulation or such. Let us look at that. So here where we expect most of the aluminum to precipitate out, let us say 6 to 8 and 4 to 5. So you see sweep coagulation occurring, right. That is what we see here, and optimal sweep, they have a particular location here. And here looks like charge neutralization to zero zeta potential with AlOH thrice solid. So that also seems to be happening, right, different ways, and charge neutralization to zero zeta potential with a different kind of solid, let us say, right. So here it is adsorption destabilization. Again, depending upon where we are, we will have different kinds of destabilization. So only sweep or combination of sweep and adsorption, so that takes place here. So let me move on. So here you obviously have the amount of alum that's being added. So this is in milligram per liter and this free metal concentration is here. So I am assuming this is total metal, but let's leave that there, right. So with another common coagulant which is used, it's ferric chloride, ferric Fe3 plus, ferrous relatively reduced Fe2 plus. That's something to keep in mind. Here it's 3 plus, let's say it's Fe3 plus and Cl minus, right. So that's why you need for charge neutrality for every 1 ferric iron you need 3 Cl minus, 3 chloride. Again, let's not go into that. So when I add it to water, what will happen? Dissociation or dissolution Fe3 plus and 3 Cl minus. But we know that Fe3 plus will not stay as Fe3 plus, but will form soluble hydroxides or it will precipitate out, right. So again, same case as aluminum, that is what you see, you have the soluble complexes being formed here, right. OH1 and 2 plus charge, OH2 and plus 1 charge, right. Again here also pH will decrease because H plus is being given out. Thus, you need to have some alkalinity in the solution. Again here another predominance area diagram, but this time for Fe3 plus. And again you see that what is predominant in the neutral pH range at most working iron concentrations or ferric iron concentration, it is the solid, let us say ferric hydroxide that is precipitating out, right. And obviously at higher pH you are going to have the complexes predominating. Again, that is something to keep in mind. And then here what do we see? So Fe total, right, and such, but again sweep coagulation, because this is where precipitation is taking place. So that is one thing to keep in mind. And restabilization zones, changes with colloid or surface area, we will not go into that. Again, for most working ranges, this is the concentration we are looking at and this is the pH. So we are going to have sweep coagulation, but you can also have adsorption based destabilization too, right. That is something to keep in mind. Let us move on coagulation using ferrous sulfate. So ferrous, you can add ferrous by without changing it or such, so that you can neutralize the charge. That is one aspect. Or people sometimes add Fe2 plus to get to Fe3 plus, but Fe2 plus to Fe3 plus, how do you go from there, let us see, right. This is the half reaction. So you have to take out this electron, and this electron will be accepted by oxygen or by chlorine, right. Again, I am not balancing it, so you can do that. So Fe2 plus can be added as Fe2 plus itself, so that it can neutralize the charge. It won't precipitate at almost all or usual operating pH and concentration ranges. But if you want to use Fe2 plus as a source of Fe3 plus, obviously you can let it be oxidized by the oxygen or add a oxidizing agent. But again, this is relatively rare, right. So this is what you have, obviously Fe2 plus, and now it is becoming Fe3 plus, right. So here we seem to have a simple problem. Let us try to go through this. Again, whenever you are solving these problems with stoichiometry, note that there are 3 or 4 major aspects. I will try to maybe touch upon that, and you can use that as a basis to solve it either your own way, or maybe use these tools to solve in a much easier or in a non-cluttered fashion. Let us see what we have. A chemical supplier reports that the alum that he has, stock alum has, is 8.37 as Al2O3, right. Never 100% purity or what I want, right. Here he has some stock alum chemical, and in that 8.37% only is present as Al2O3, and specific gravity is 1.32. Specific gravity as in gravity, not gravity, density of the particular material to the density of a reference, typically water, let us say. Specific gravity of that particular chemical is 1.32. For this stock chemical, we are obviously going to look at calculating the concentration of Al3 plus, just the metal, free metal in that particular stock solution, right. And the alum concentration, if it is reported as grams per liter as this Al2SO4, this the alum concentration reported as. So here we see that molarity, meaning we want to express the units in terms of moles per liter, right. In general, chemists and such will understand this. I prefer molarity, let us see. Some people would prefer it to be expressed in terms of alum, as in layman or people who are working with mostly engineering applications. They do not want to look at what is the Al3 plus free metal concentration, what is the Al3 plus that is precipitating out. They just want to look at how much alum do I need to add if I want to achieve my level of coagulation and then flocculation, right. So units are sometimes expressed as the amount of or mass of alum per liter that needs to be added. So, right, you are going to have such units too. So, right, it is reported as grams of Al2SO3, SO4 thrice dot 14 H2O. And also for a 30 milligram per liter alum dose, with a flow requirement of this, right, say, right, calculate, we will look at that. So, this concentration is required for a particular flow that is coming. Calculate the chemical feed rate, what is the concentration of the chemical or such that I need to, not concentration, for water is coming in. Water is coming in and I want to see to it that the mixed one has a concentration of 30 milligram per liters of alum, let us say. Here let us say assuming there is nothing, and so how much or what is the rate of this pure chemical that I need to add. So, I have Q1 and Q2. Q2 has alum, Q1 has 0 concentration of alum, Q2 has this concentration of alum. So, both will mix and finally, I will end up with this 30 milligram per liter of Q1 plus Q2, let us say, right. So, this is what we have. Yes. So, how much is this feed rate? How much feed rate do I need? And alkalinity consumed. So, if I am adding this alum to the water, how much alkalinity will be consumed, right. So, we can also look at that. How do we look at this? For this, we will look at the relevant reaction that happens when we add this compound to the solution. From there, you can know how much H plus will be given out, right, equivalents, right. Then that will be equivalent to the H alkalinity that will be consumed, because in the alkalinity equation, you know that there is a term minus H plus. So, that is how you will calculate alkalinity, let us say. And the amount of precipitate produced in milligram per liter, usually this is rarely used, and kgs per day, this is usually used. Why is milligrams per liter not a good way to look at precipitation? Because when we say milligram of some compound per liter, it typically means milligram of, let us say, sugar is dissolved in this solution of 1 liter. But to say that something has precipitated out and that is per liter does not really work out. So, then you have to clearly specify milligram of this sugar or this particular aluminum hydroxide has precipitated out from 1 liter of solution. So, that is something that we need to be clear, and obviously how much mass of the aluminum hydroxide has precipitated out per day. So, different units, and how much NaOH, NaOH meaning NaOH will go to Na plus and OH minus. Typically pKa is such that this is almost always this way. So, we are adding a base, would be needed to be added to counteract the consumption of alkalinity by alum. So, here we are looking at alum consumption. So, if I do not want the alkalinity to decrease, how much NaOH should I add? So, again that is pretty straightforward. OH minus, you know the alkalinity equation, it has one OH minus, right. One equivalent of alkalinity will increase per 1 molar addition of OH minus. So, from that we can calculate it. So, let us get this done or look at it in a bit more detail, right. So, what is the first aspect? Molarity of Al3 plus. So, I want to be able to calculate Al3 plus molarity. For that, I need to know how many moles are there of Al3 plus per liter of my water, 1 liter of my solution, right. For this, obviously, I need to know molecular weight. What would molecular weight give me an idea about? It will give me an idea about grams of Al3 plus per 1 mole of Al3 plus, right. So, how much is this molecular weight? So, this will be required, and obviously, then if I have the mass of that particular solution, I can use this molecular weight to get the Al3 plus or such once we look at the stoichiometry. So, let us get that done. So, here we are calculating the molecular masses of the different compounds of interest. Obviously, Al2O3, that was asked in the question, Al2SO4 thrice dot 14H2O, because in part B we were going to look at, or we were asked to calculate it in the form of as Al2SO4 thrice dot 14H2O per liter. How much of this will have to be added if I want to get a similar effect? And again, this is the solid. So, this is the solid in this context, it is not the complex, right. So, this is the solid. Again, we will calculate the molecular weight and also of NaOH, right. And for that, molecular masses of the relevant elements Al3 plus, right, and sulfur, sodium and such, we have them. So, in general, in the exam I might give the usual unique ones, but usual ones, let's say oxygen, aluminum, hydrogen, these you should be able to come up with yourself. So, let us see the approach for Al2O3, 2 times 27 plus 3 times 16, right. So, you have that simple algebra, and similarly we are calculating the molecular weight of each of these compounds of interest which we identified out here, let us see, right. And LOH thrice. So, alum, as you see, it adds considerable or it is considerably heavy per 1 mole. So, that is what you see, 594 grams per 1 mole. Why? Obviously, you have a lot of sulfate, let us see, right. So, that is one thing to keep in mind. And what is the molar concentration of Al3 plus in the stock alum chemical? Let us see how to go about it. So, first, what is the density of the stock chemical? I know the specific gravity as in density of the stock chemical referenced to the density of water. I know the density of water. From that we can calculate it. This is the specific gravity, density of the relevant water, which we are assuming to be 1 kg per liter. So, the density of that particular solution, stock chemical solution, is 1.32 kg per liter, let us see. And the concentration of alum in the stock chemical as milligram per liter of Al2O3, right. And I think we know that around 8.37% or something was present as Al2O3, right. Yes, 8.37%, 8.37 by 100 is 0.0837, let us see, right. So, this is present as, or this much of your particular solution is present as Al2O3. So, I have 1.32 kgs of that stock solution per liter, but I know that 8.37% is the Al2O3, right, by mass, and then 10 power 3 grams per kg. So, what do I have? I now have the mass of Al2O3. So, I have 110 grams of Al2O3 per liter of my particular chemical. So, that is what I have, right. From this we will be able to calculate the molar concentration of Al3 plus. Okay, I just am giving the question again, so that at regular intervals, so that we can follow what is happening. So, let us move on. It will be useful later, maybe not much now. So, let us look at the next aspect. We calculate the relevant molecular weights and got the relevant mass per volume, right. We have different units or ways of expressing units. One is mass per volume, as in gram per liter or milligram per liter and such. Another unit which we typically want to use based on the stoichiometry is moles per liter, right. How do I go from here to here though? So, I have grams or mass, okay, grams per liter of, let us say, what is this, Al2O3. If I want to convert it into units of moles per liter of Al2O3, what do I need? I need moles of Al2O3 in the numerator, right, and in the denominator I need something that will cancel out this term or mass here, grams of Al2O3. And I have a relationship that gives me the moles per particular mass of the Al2O3, that is the inverse of molecular weight, right. So, that is how you can go from mass units to molar units. Here we are first using the mass units of Al2O3 which we have, yes, and then we are converting that into the molar units. That is what we did right here, and then I am concerned with the Al3 plus molar concentration, not the Al2 plus, not Al2 plus, pardon me, Al2O3 molar concentration. So, looking at Al2O3 and Al3 plus, I can see that there are 2 moles of aluminum per 1 mole of Al2O3. So, that is why 2 moles of Al3 plus for 1 mole of Al2O3. So, this 1 mole of Al2O3 will cancel out here, yes, and let me use a different colored pen, and this mass will cancel out here, grams of Al2O3. So, what am I left with? I am left with moles of Al3 plus per liter of water. So, that is what I have. This is moles of Al3 plus per liter of water, right. So, it is just using the molecular weight and looking at the stoichiometric ratios, and it is pretty simple. Maybe in one of the other examples we will look at equivalents typically in terms of charge or electrons or alkalinity, but we will come back to that and look at it, right. So, that is one aspect to keep in mind. With that, we are able to calculate the molar concentration of aluminum. So, next aspect, okay, we want the units now to express the same units, we want them to be expressed as Al2SO4 thrice dot 14H2O, which is the typical formula for alum, right. So, here we are going to assume that maybe you can look at the equation for 1 mole of alum, the equivalent, or it will be proportional to 1 mole of Al2O3, right. So, that is what we are going to do. And what do we have here? We have the 110 grams of Al2O3 per liter of water. If I divide that by the molecular weight, so what do I have? 1 mole of Al2O3 per 102 grams of Al2O3. So, in effect, I am dividing by the molecular weight. So, from here I will have the molar ratio, right. And here we are saying that it is 1 mole of alum for 1 mole of Al2O3. So, I will then say 1 mole of alum per 1 mole of Al2O3, right. So, here the units are not asked in terms of moles per liter of alum, but mass per liter of alum. So, I need to convert moles per liter of alum into mass of alum. How do I do that? I will multiply with the molecular weight of alum, right. So, molecular weight, what is this? Looks like it is 594 grams of this. When I say alum, I am referring to this particular formula, molecular formula, grams of alum per 1 mole of alum, right. So, what did we do? Mass units to molar units, then the molar ratio, and then again molar what do we say, units of alum to mass. So, that is what I have. It looks like I will end up with this 643 grams of alum per liter. So, again in general, what does it tell me? If I want 110 grams of Al2O3 per liter, I need to add 643 grams of alum per liter, right, or vice versa. So, that is what it means. So, we are done with this. Next aspect, okay, this is with respect to the feed rate and such. We have water coming in, the flow rate is given. So, let me say that this is Q1 and the concentration of alum here is C1, and I am having to feed a concentrated flow of or concentrated alum to this solution. I am going to call this feed, Q feed, and concentration of alum in this is C feed. After mixing, it is now going into this, which is Q mixture, or here we are referring to that as Q process. So, let me use the same subscript, Q process, and final concentration of alum in the process, right. So, what is happening? Two streams are coming in, one stream with the most of the water with no alum, and one where we are adding the feed, let us see, where I am adding the alum as the feed. These two are mixing, and then you have the process. We know the concentration at which it is supposed to be at. It is supposed to be at 30 milligram per liter, right. Anyway, we will come back to that. So, how do I get this? It is just simple mass balance. Mass coming in is equal to the mass going out, right. So, two streams joining. So, mass coming in is, this is on alum, Q1 C1 plus QF CF. This is the mass of alum coming in, is equal to QP into CP. Here the way that it was calculated, they are assuming that QP is almost equal to Q1 because Q1 is far greater than QF. But in general, though, as you can see, QP will be equal to Q1 plus QF, right. So, what do I have here? I need to be able to solve this equation now. Let me see what we have out here and we will go through. I have this flow rate which is given. I know that there is no alum coming in along with this flow. So, this C1 is 0, right. This is the QF I want to find out. CF I found out from here, right. CF was found out. Yes, this is what we are using. CF was found out, and CP was mentioned. I think it was mentioned as 30 milligram per alum, and QP I know from here, right, either this way or this way. In general, I would always suggest that you use this and not make assumptions, right. Though we use this here for now, in general always assume that or calculate the flow rate based on the relevant aspects there, right. Do not assume anything. So, we are just left with one unknown, which is QF, and I can calculate or solve for this equation, right. So, we just plug it in, this term goes to 0, I can substitute the relevant variables, and I see that I need to add 1.40 liters per minute, or the flow of alum should be at 1.40 liters per minute, and the concentration has to be at 643 grams per liter of alum. If I want a concentration of 30 milligrams, this is 30 milligram per liter of alum, which has a flow rate of what, 43,200 meter cube per day. So, for 43,200 meter cube per day, right. So, that is the relevant aspect, it is just mass balance here. Let us move on. So, we are done with this, this is just change in stoichiometry, same case here, and here it is just simple mass balance. And what is the alkalinity consumed, right. So, what is the approach here? We know the alkalinity equation. Alkalinity is equal to the sum of all the bases. Typically, we are assuming it is only carbonate system that is predominating, right, plus CO3 2 minus 2 times CO3 2 minus Y. As you can see, CO3 2 minus can take 2 H plus, right, minus H plus. So, what does this mean? If I add 1 mole of OH minus, alkalinity will increase by 1 equivalent per liter. Same case with HCO3 minus. But if I add 1 mole of CO3 2 minus, because of this 2 equivalents, alkalinity will increase by 2 equivalents per liter. If I add 1 mole per liter of H plus, meaning alkalinity will decrease by 1 equivalents per liter. So, that is what it means, or that is what we can understand out here, right. So, let us take this through and let us look at the relevant equation. And what is the amount of precipitate produced? So, for this you will have to look at the relevant equation or the reaction, we will look at that. And how much NaOH has to be added if you want to see to it that the alkalinity is not consumed. So, let us look at the equation. Alkalinity consumed, it's this is what we have. So, if I am adding Al2 or alum, aluminum hydroxide is precipitating out and sulfate will be released and H plus is being released. So, pH is going to decrease or H plus is going to be released, and we know the equation for alkalinity. Alkalinity is equal to, just for the sake of understanding I am writing this again, even though I wrote this out in the earlier slide, minus H plus. So, if I am adding H plus, alkalinity will decrease, right. So, we already have it. So, for 1 mole per liter increase of H plus, 1 equivalent per liter of alkalinity will decrease. But here we are adding, the ratio is here is 6, but we will look at that, right. So, let us see what we have. So, alkalinity, so we looks like it is in 30 milligram per liter as alum, 30 milligram per liter as alum, right. And I want it to be converted into equivalents as CaCO3. The answer was asked in terms of as CaCO3 per liter. Before that, I need to get it in terms of equivalents per liter, right. Before that, I need to get it in terms of moles per liter. So, only then I can go in this direction and end at my answer. So, first this alum I have to convert it into molar units, right. So, molar units, what do I do? It is 1 mole per 594 grams of alum, right. So, now the units are in moles. And I know that for 1 mole of alum, 6 moles of H plus are being given out, 6 moles of H plus per, here also I should write alum. Why do I like the way that I am writing? Because here I can see now moles of alum cancel out, mass of alum cancels out, and I am left with moles of H plus per liter, right. So, that is why I like to write this moles of alum or moles of H plus or specify that clearly. But I want it in equivalents per liter of alkalinity, and I know from what I see that it is 1 equivalent. So, that is what I have here. So, 1, I guess I should have written it in the inverse way, right. This should have been divided by here maybe, and this should be into, anyway we can always correct it. I know that 1 equivalent of alkalinity will be consumed per 1 mole of H plus being produced, right. So, that is what we have. Now, the units are in terms of equivalents per liter of alkalinity. but the units are being asked in terms of as CaCO3. How do I convert that? So, molecular weight of CaCO3, it's 100, right, 100 grams, N is 2, right, Ca 2 plus charge or CO3 2 minus charge, N is equal to 2, right. So, equivalent weight will be 100 by 2, which is 50 grams. So, that is what we have, 50 grams of CaCO3 per 1 equivalent of alkalinity. So, I have to multiply that, 50 grams of CaCO3 per 1 equivalent of, let us say, alkalinity, let us see. Yes, again in terms of alkalinity here. Okay, so okay, here I see that it's not with respect to charge, but CO3 2 minus, but even then you can see that it's 2 is the relevant factor. So with that, I will get my relevant answer, 15 milligram per liter as CaCO3, right. So with that, I'm done with the alkalinity consumed. Precipitate formed, same way, I will look at the relevant reaction. So 1 mole of alum, 1 mole of alum, 2 moles of precipitate, right. So that's what we have. Again, alum, we are converting it into molar units, and I know that there are 2 moles of this solid, this should be mentioned as solid, precipitating out per 1 mole of alum, that's what we see from the stoichiometric ratio. And I know the mass of AlOH thrice, which is 78 molecular weight, right. And now I will get this, but what does this mean? It does not mean that there is 7.88 milligrams of aluminum hydroxide, the solids dissolved in water. No, it means that, anyway, the way we calculate it means that this amount of aluminum hydroxide solid is precipitating out per liter of your solution. That is what it means. And then again it was asked to transform this into units of mass per day. So here I have mass per volume units, that is what I calculated, mass per volume. So if I want it in terms of mass per time, I obviously need to do what now? Multiply this by volume per time, and volume per time is flow rate. So that is what you multiply it with, and you are going to get your 340 what is this, kgs per day, I guess, right. So let me move on. And NaOH, how much NaOH is required? There are 2 ways to go about it. Earlier we looked at the equivalence or concentration of H plus, we can use it until here, this point, and then transform it into NaOH, because I know that 1 H plus and 1 OH minus, 1 OH minus meaning 1 NaOH, right. 1 for every H plus, 1 OH minus has to be added. So in this way I can look at it and take it from here, or another way to go about it is obviously to write the equation such that it directly reacts with NaOH. So again you see that for 1 mole of alum you have 6 moles of NaOH. Let us take this approach, 30 milligrams of alum per liter and molecular weight division to get the molar units, and here I see that for 1 mole of alum 6 moles of NaOH are required. So 6 moles of NaOH per mole of alum, and then the molecular weight of alum, so that I get the units in terms of NaOH. So with that, we are done with this particular session, and I thank you for your patience.